Hello everyone. In this video I'm going to show you a nice trick that I found on my calculator. It's about the power of numbers, and if you take for example the powers of 2, you have 2 and then you have 4, then you have 8, and then you get 16. So let's take away the 1, so you have 6, and then you go back to 32, so you go back to 2 and then 4 and so on and so on. So if you 9 times 3, 27. You remove the 2, you get 7. And then 7 times 3, 21. You have 1, and so on. So you have a square pattern again. If you take 7, you have 9, 3, 1, 7, etc. You have 8, you get 4, 2, 6, 8. So that's quite interesting thing. Why does it do that? If you have 4, it doesn't really work like that. So you have 4, 6, 4, 6. If you have 9, you have 9, 1, 9, 1. When you have 5, 6, or 1, they always stay stationary. So I want to show you what's happening actually. So I made a little program in MATLAB showing these different patterns. So if we start from 2, we get 4, 8, 6, etc. So we have this diamond shape. With 3, we have this square. With 7 as well, 8 as well. And then we have this line, these lines for 4 and 9. And for 5, 6, and 1, we don't have anything because they always stay stationary. Now the idea would be, what if I just increase the grid size? So instead of a 3 by 3 grid with a base 10, I increase it to a 4 by 4 grid with a base 17. So let's go ahead and do that. Okay, and let me remove the text. Okay, so we see that these patterns stay like that. So we have these squares on the corners, and now we have even more beautiful pattern that emerge, and they're all at 90-degree symmetry. Why do we have this 90-degree symmetry? After all, it's just a grid between from left to right, from bottom to top. So why do we have this 90-degree symmetry? And what we also notice is that we have some duality between numbers. 5 and 7 are duals, but they don't go into the same direction. They're at opposite directions. 6 and 3 are duals. 8 and 15, 14 and 11, 10 and 12 are duals. 9 and 2, 4 and 13. So there is a quite interesting thing happening here. Now let me go ahead and go to a 5 by 5 grid. So you see again more interesting shapes. And now you see that we don't always have 90-degree symmetry. This one doesn't have any symmetry. And sometimes you have 180-degree symmetry. We can keep on increasing the grid size and have more and more shapes. And some of them are 90 degrees symmetrical, and some aren't. 7 by 7 grid. Some of them are really beautiful, like this one. It reminds me of some different fractals. And then 8 by 8 grid. You always see that, for example, this 8, this corner always go to this corner and then goes round. Let's go ahead and go to the 9. This flower shape is quite interesting. And then when we increase the number, it starts becoming a bit scrambled. Some shapes are still interesting, but others are a bit more scrambled, like this 46, for example. So we start seeing less and less shapes, and it becomes smaller and smaller. So I'm going to just stop here and try and explain why we have sometimes a 90-degree symmetry. Okay, let's start with a 3 by 3 grid. And so you have this grid here, and let's take the opposite of each number and put it back on the same grid representation. And let's take modulo 10. So we take this modulo 10. So what you see is that we have the same original grid, but rotated by 180 degrees. So just by multiplying the original grid by a constant factor of -1 will give you a rotation of 180 degrees. Now if I do the same thing, but by multiplying it by n, which is the width of the square, so in this case by 3, you will see that, funnily enough, you have a 90 degrees symmetry, a 90-degree transformation, which is quite weird. If you think about it, just by multiplying this by a constant, you have a 90-degree transformation. 1, 2, 3, 4, 5, 6, 7, 8, 9. I can also do the same with a 4x4 grid. It will give you the same thing. So if I copy this and I multiply this time by a 4 and take modulo 17, you will see that you always have a rotation of 90 degrees. So think about it. Why would that be the case? It's quite an interesting thing to think about. Now this means that, for example, if you start with a 3 and it goes to a 9, the value of 3 rotated by 90 degrees would be 12, for example. So if 3 goes to 9, 12 would definitely go to 2. Okay, because we only multiply this by a constant factor of 4. So wherever 3 goes after that, 12 will go the same way with a rotation of 90 degrees, because we only multiply it by a factor of 4. And it's the same case by multiplying by -1. It will be wherever the 3 goes, the opposite of 3 will go to the opposite of 9. If 3 goes to the 9, the opposite of 3 will go to the opposite of 9. Okay, so if during the travel of the cycle of 3, for example, we go left and right and up and down, and then it arrives to 12, for example, then you will know that the rest of the travel will be exactly the same as the original travel, but with a rotation of 90 degrees. The same will happen if we bump into 14 or 5. It will always have a symmetry of 90 degrees or 180 degrees. So when you take the case of a 4x4 grid, you will always have a case where when you start from a number, you will always bump into the 90-degree rotation transformation of the same number. So you always have a 90-degree symmetry. But if you go to a higher value, like 5, sometimes you will bump into the symmetrical value, but sometimes you won't. Sometimes you will go directly to the 180 degree, so to the opposite, without passing by, for example, in the case of 4, you will not pass by number 20. You will directly go to 22, to the opposite of 4. So in this case, you will have a 180 degree symmetry. And sometimes you will never bump into the symmetrical values. So for example, in the example of 3, after just 3 steps, you will go back to 3. So you will not have a symmetrical shape in this case. So some symmetrical shapes occur because of that interesting properties. When you have a base of n squared plus 1, and you organize the numbers in a grid, then multiplying it by n will give you a rotation of 90 degrees. And that's why these symmetries, these nice patterns emerge, which is quite an interesting thing. So that's all for today. If you like the video, please click like and comment. If you find anything more interesting about that, I will share the MATLAB code in the comment in the description of the video if you want to play with it, and it's on GitHub. And thank you for watching.